Hello, we are back to the fourth clip of our fast Fourier transform lectures. Okay, and today we're gonna move you to using a different platform to solve this classical fast Fourier transform computation. Okay, and this platform is what we call the Matlab. Okay, which is available. Okay, if you're using your KU Google Gmail code. Okay, you are eligible to be able to install it because our university do receive the campus license. Okay, and first thing that you need to do is that use your Gmail address, okay, to install, okay, Matlab. Okay, just type Matlab installation. Okay, they will ask you about your ID and you're using your Gmail code. Okay, and once your Matlab has been installed, I haven't updated yet. I'm still using the 2020 version. Okay, and as you can see on your screen here, okay, this is a very simple program that we're gonna call. The first statement is that we're gonna call the uh, file name what we call Excel FFT 16,384. This is a file that I implement under Excel platform. Okay, contain 16,384 data, and it's contained in sheet number one. Okay, sheet number one, and the range that the data installed is A1. Okay, from column A. Okay, from row number one to row number 16,384, and then we just use this command xls read. This is the way that you can import, okay, the data from Excel to the Matlab. This one is mean that, okay, search this file name, okay, on the default reference of the Matlab, okay, which is in this case is a download. Okay, it will be the download drive. Okay, and then the sheet number. Okay, this is sheet number, sheet one, and the range of the data. Okay, therefore they will extract all the data concerning to the address that you refer from for the file and also the reference file. Okay, and put it in the vector called data x. Okay, over here data x, and then you can have this one, the very simple. Okay, even simpler than Fourier analysis in Excel is that there's an object command we call FFT here. Okay, you use FFT, okay, bracket, and the data. This is a time domain data x. Okay, put it in the bracket here, and then using the object FFT. Okay, under the Matlab. Okay, and you get FW. FW is certainly the output for the frequency domain. Okay, first of all, we're gonna go back to a file that I already, this one we call Excel FFT, what is it, 16,384 solution SOL solve. Okay, and which I already explained to you from the previous script. Okay, previous script, and then we did solve the problem over here. Okay, this is a problem of 16,000 uh, 384, but n start from 0, so it's end up at 16,383. Okay, so contained in sheet 3. As you might remember that the first two sheet is just solving a sub problem of 8,192. Okay, the separate, and to solve 8,192, okay, we're using the what we call the idea of radix 2. Okay, in a block form. Okay, this one. Okay, suppose you have first, in the first equation you have 16,384. You separate two terms. To one of them is 8,194, 8,194. But in the Excel, as you might recall, that we can only solve the problem up to, okay, if you consider in sheet one. Okay, in sheet one over here that we explained from your last script. Okay, we have a problem, okay, with this yellow zone. Okay, that contain 8,192 data. Okay, and we'll be able to solve this. Okay, this is the results. Okay, but we haven't checked the solution for from other software yet. But we all know that, okay, for 8192 we can separate them. Okay, okay, by using this we start with this example. If I remember 64, okay, we separate into part of 32. But in this one, okay, we separate the data here from over here down here. Okay, from row 107 here. This one is the data start from here. Okay, there's two examples in the same sheet, each one separate on two part. Okay, 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 this one, the even term and the ordered term. Okay, and odd order term. Okay, and each of them, all this value, you can use Fourier analysis to solve it. Okay, so with this Fourier analysis, okay, you can based on the idea of Kulituki's, okay, idea. Okay, you separate these two. If you can solve each of this, okay, you can use this formula. Okay, these two. Okay, to find the whole, the twice a larger size problem. Okay, and that's what we did in this sheet. Okay, so with 4096 we'll be able to solve 8100, no, over here we can solve 8193, 91, 92. Okay, but on sheet 3, okay, actually this is the new data that keep changing every day, every time. But if you want a fixed data, okay, you can find it in this drive that I show you, that we have a test data over here, that FFT test. Okay, over here 665. This is one of the homework. Okay, and from the last sheet we already expanded to 7000 something, which is 3 by 3 by 8192. Okay, that's beyond I didn't save the data for you in this drive, but you can use the Excel file to generate it. But this is the data, the Excel file. Okay, corresponding, this is for FFT for 16,000. Okay, this is the original data. Okay, 16,000. Okay, you look at the Google Sheet over here. Okay, this is the data that they import, the data. Okay, here. Okay, we're not gonna. Okay, and this is for the problem of 81,092. Okay, this one we look at the Google Sheet. Okay, so this is a fixed data, not rely on the formula. Okay, but if you want to generate the new data for an extensive problem, okay, you can go back and use this file, okay, of FFT big data here. Oh, I'm sorry, here. Okay, this one is changing every time because the formula is still there. Okay, but in this one, in this file, from last time that I show you that we didn't save it. Okay, we still finish at 6536. Okay, but you can keep generating, and one of the homework, as I might recall you again, we want you to solve this side problem, 3 by 3 by 8192. Okay, and that's the result of 73,728. Okay, and why we use 3 by 3? Because we want you to apply the working sheet here, because we did radic tree over here. Okay, so to solve this problem, you need to use the platform of 8192, and then you double use of the radic tree on sheet 2. Okay, and but overall is that once you solve the problem, how do you know that the solution that you get is a correct solution? Okay, so that's why we have to introduce you an alternate software here. Okay, like in this one. Okay, I already install download the Google Sheet and change it to Excel to the download reference here, and with the file name called Excel FFT 16,384. Okay, and I already explained this, and the result will be here. Okay, first of all, we're gonna try to solve this problem. Okay, we solve it, we run it. There's a command here. Okay, command window here, that will show you that how the result gonna come out when once you execute the program. Okay, the content in the Matlab, there will be exist the the page of the editor to write a sequence of code, and then to run the program you have to move to the command window, and there will be several options over the at the above of the software for you to choose to execute. Okay, and you see in the bottom of your left here, a very short small one we call BC. BC is mean that they're still working on this problem. They need to import the data from this file, and then they're gonna execute this one. The first time running normally take a while. Okay, but once the problem, yeah, like in this one is already done. Okay, this one you see that this one we call this, and then its execute is finished. You know that the resulting, okay, we might check for you a little bit that, okay, suppose that I'm gonna do data x, okay, from the first row, okay, column is go to the 10 row, okay, the first 10 row, and with add this, okay, this sign called that transpose, because I want them to just show instead of the as a column vector. Okay, I will move it to row vector so that you can see the data clearly. Okay, this is the first 10 data for the data x that we uh, just import from this file. Okay, we import from Excel FFT 16,384, and then I press enter. Okay, so they start here 0, so and so on. The first 10 data, we're gonna check this data to this file. Okay, for this since we already find the solution last time. Okay, and the original data is here. Okay, you can see that it's 5, 8, and so on. Okay, 5.48. This is the data for 16. Oh, no. Huh? Oh, okay. It's a different file. I should look it here. Okay, that's correct. But why is only? Oh, it's not sheet 3. You have to go on sheet 3. Sorry. And that's sheet 2. Sheet 3 is here. The first 10 data is here. 0, 5. You can see that up to 9, 0 to 9, 5.428, and you go back to the Matlab to 0, 5.428, 8.967, or 8.4, and you can check this. It's the same data set, but just the first 10. Actually, you have to check it all. Okay, but okay, I just check you for some sample. Okay, okay, here. The last one is 0.6999. Okay, there's 0.69. So it's the same data. And now we can check the solution. This is after they execute the fast Fourier transform. Okay, suppose that I'm going to check FW, okay, of 1 to 10, the first 10 data, and then I press enter. Okay, this is a 10,000, and you need to multiply this number with 10,000. The first number you can see this all the first 10 data. Okay, the first one is 5.3514 times, okay, times 10,000. Okay, so it will be 53,514. Okay, so we go back and take a look at the solution here. This one, 53,300. 514, 30 this more accurate there. Okay, but you can increase accuracy for the Matlab also, but well, we it's just a problem, and there's no imaginary part I. They're using I here. They didn't use J, just like what we did. Okay, because this is a real notation in mathematics, and you might recall I is equal to square root of -1. The second one is minus here, plus, and remember that you need to multiply this by 10,000 over here. Okay, it's a unit, and then you go back here. Okay, this is the second one, minus 16 plus 5394 here. Okay, you can go back and look here, minus 16, right? Once you multiply by 10,000, it becomes 16. This one is become 54. Okay, and you go back and look at the Matlab result. It become 53.9, rounding to 54, minus 16. Okay, The third one is minus 153.13 and minus 144, right? And then you go back and look at the math solution there, here, minus 153 minus 144. Okay, so this is a way to confirm that the solution is correct. Okay, actually you need to check all of them. Okay, there might be but I already checked all of them, but this is just an illustration to show to you that the way we come here is correct. Okay, but you might recall that, okay, over here we find under spreadsheet format we have a hard time to execute this number. Okay, because the limitation of the Fourier analysis that can go up to only 4096 number of point solving. Okay, there's a maximum limit. Okay, that's why we need to go back to the basic foundation of Fourier by Fourier by applying this, so that we can extend the problem solving capability under Excel format. But then now we already checked that. Okay, you might say that, okay, I'm not sure, that's only the first 10 data. Okay, suppose we go back. I'm gonna show you. Okay, I'm gonna go with FW of okay, the last data should be 163 384. Okay, and then before that, okay, colon. Okay, and then we got a 163 375. Okay, let's just say I'm gonna do the last 10. Okay, oh, 384 FW 163 384. Oh, so I just put too much. This 16375. Okay, up to 16384. Okay, so and we need colon between this. Okay. Okay, this is the last 10, multiplied by just only 100. Okay, remember that this become the additional unit, the last 10 value of FW, this one. And we can go back and take a look at the result for this FFT, the last 10. Okay, this is the first 10. We go with the last 10 value. The last 10 value is over here. Start from 75, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay, you have to start here because the rounding. Okay, start here. One, because this one start from 0, didn't start from 1, 4. So 163.74 is equivalent to the location of 163.75. Okay, this one is minus. Okay, if you take a look, okay, I expand through. Okay, minus 148 point something, minus 146. Okay, and you go back and then look at the Matlab result, this one. You see, multiply by 100, you become 148 minus 146. This one is minus 329 plus something like 33. Okay, for some, you can see the next value here for the solution, minus 329 plus 33 over here, and then minus 218 minus 1.43, the next one. Okay, you can go back and look at the Matlab results. So this one is minus, okay, this one is 218, right? Then this one 1.44. Okay, minus minus, which is equal here. Okay, that you are interested. And 163.285. okay, minus 406, and then you get 16, this one 100. Remember that you need to multiply 100 here. This become 163. This is minus 406, and the last value is minus. This one should be 163, and the other one is minus 100, 539. Okay, and then you now look at the solution here. The minus 16 minus 53. Okay, I make a mistake here. This because it's multiplied by 100 should be 16. Okay, 0.36. This one 53. Okay, and you get over here, get minus 16 minus 53.9. Okay, so we check the first 10 and the last 10, but actually if you check all of them, you get that the solution is pretty close together. Okay, so it's mean that this one work. Okay, you can use Matlab as a comparative study of the result from you doing or whatever you do on the Excel platform. Okay, by using by creating a file here as a remember the input data here. Okay, and make sure you put in sheet 1 and then identify the range of the data, and then this one, the fourth is a command that you can call it and then put it in some specific vectors, and then you just use the object, very easy, FFT of that object. You get the results of the Fourier transform here. Okay, and you can see that the size under Matlab is much very convenient to do it. You can check the result from all of them. Actually, this file is already contained in I think in the over here in the Google Drive here. Of the, you can FFT here, FFT here, and then the file, if you want to check it, this is the file FFT check. Okay, it's the same file. Okay, that you can use. Okay, the same file that is in the Matlab. I already put it in all in here. Okay, that you can retrieve it. Okay, okay, and the FFT big data, and then this is the solution file. Okay, of FFT is already here, and then we have I already set up the 65536. Okay, but remember that, okay, we have an additional assignment for you over here. Okay, for this data in sheet 3 that we want you to expand it to I forgot already what, 3 by 3 by 8192. Okay, with 673,728. Okay, make sure that you, okay, you expand this. Okay, 73,000. Okay, you go to 73,007. Okay, you can do it. I think it's nothing difficult here. I'm not going to do it for you. Okay, okay, just keep expanding the data here by up to the cell here, 73,728, and then applying the knowledge that under Excel platform to find the solution. And then now you can have a Matlab over here. Okay, you can import the data to the Matlab environment, and then you can solve it to check whether two solution is the same. Okay, that's the introduction. So to execute the fast Fourier transform in Matlab, is if you directly solve it, if you doesn't have a very long stream of data, okay, you can do it this very pretty easy to do. Okay, okay, and you might wonder that, okay, if in what case that gonna cause you some problem. Okay, I'm gonna add a file here. Okay, for you to try. Okay, so like suppose that you have a very large scale data here. Okay, I'm going to put this when use this plus, so you can add a new script of the editor. Suppose that n is the number of data. Suppose the nice thing about Matlab is that, as compared to using the Excel, is that Matlab doesn't require any n to be in the power of 2, just like Matlab. Remember that Matlab, you need to have data only 8, 16, 32, 64 in term of power of 2. But for Matlab, suppose that I want to do like maybe 500,000. Okay, suppose that n is 500,000 here. Okay, I'm gonna write a code for you so that you can follow. And then I'm going to have maybe xt as a time domain. Okay, I initiate xt as a zero value. Zero value is kind of, you want to occupy. This is a space you want to occupy in your memory. And then I'm going to say that zeros, n, comma, 1. This is the way that you implement the matrix. Okay, but this one is vector because it's only one column. Only one column, and you have n number of rows. There's 500,000 rows here over here. And then, okay, I'm going to try to generate something. Okay, maybe for j is equal to 1 to n. Okay, this is a loop. Okay, command. Okay. Okay, for each j, okay, I'm gonna put xt. You can now use the here over here. Xtj is mean the xt in row number j. Okay, because there's only one column. Okay. Or xtj is equal to, okay, I'm gonna do some random number, maybe tens times random numbers. Okay. And but the random number statement over here, you need to write the seed number also. This is seed number 1. You can have seed number 1, number 2, number 3. Okay, and this one you should need to change to the multiplication sign. 10 times random numbers and times sign of 100 times random number of j. Okay, let's just say increase with j. Okay, and then I'm going to round this number to all just positive value. Okay, and then round the absolute value, okay, of this function. Oh, I think I missed some bracket over here. You need one more, I think. Yeah. Okay. But before that, I'm going to round it to have only the 3-digit, okay, the 3, something similar to what we did on the Excel. And then colon, I put the colon down here, okay, semicolon down here, okay, semicolon, because if this statement execute under semicolon at the end of the statement, okay, it will not show the result. You need to type the result yourself, just like what we did previously. You remember that? Wherever I want to find the solution in FW, I need to type it and identify the location. And n is the finishing of the loop. Okay, so now this one I can generate the time domain data. Okay, it doesn't have any significance, just a random value, and it's really distributed, uniformly distributed among frequency domain, which is normally not happen in this case. Okay, normally in frequency domain, it's gonna when you change the data in time domain to frequency domain, you're gonna stuck within some specific bandwidth that really show that it's a frequency bandwidth that the signal or the time series data really have an effect on. Okay, but why other type of bandwidth you can see very small effects. Okay, okay, in this one, okay, I'm gonna change that. Okay, suppose I'm gonna x omega xw, then I'm gonna use this FFT of xt. You remember that? This is very easy. Okay, once I be able to do this, done. Okay, and I can put this the way that I can measure and in counting the time execution time by using the command we call tick tock. Okay, I put tick over here and then I put tock down here. Okay, tick tock is mean that, okay, this one is start your stopwatch and tock is stop your stopwatch, and they will show you the execution time. So in this case, I'm using this for two. I separate two part of the execution. Okay. The first one is over here. Okay. Okay, this one tick tock. Okay, the first part is over here. This part really show that how long you generate the problem. You go. Actually, in the real world, this is just I make it easy for myself that I just randomly generate anything. So it's the quickest way to generate a problem. But in the real world, you might have to retrieve it from Excel. You might have to go back and using some IoT that to from your sensor that they're gonna put your data somewhere else on the cloud, and then you need to retrieve it back to your computer. So it's gonna take some time in the real world. Okay. And the second part is the execution part. Once the time domain established, how long the FFT execute. Okay, to make it, I'm going to start with 10,000, 100,000, which is a lot already, right? Or maybe we start with small one, 10,000. And you know that this is not in the power of 2. I'm just going to say that this is only 10,000 data, okay, which already a lot, okay, even small. So I'm going to run, first of all, I'm going to save this program first, okay, I'm going to save it as, certainly the default drive is in the download. I'm going to put this file, test FFT, okay, I'm going to this Matlab, okay, Matlab, test FFT Matlab. Okay, so this is the new file over here, test FFT Matlab. Okay, and this file is not in the Google Drive that I showed you previously, because I just write this to show you how to manipulate the data and how you solve it directly, not without using any additional knowledge, because FFT is like a black box down here. Okay, so I'm gonna run it. Okay, so test. Wow, 10,000 data. You can see the results down here. They will show that it took 0.15 seconds to generate the prompt, and to solve it, it's even where what 0.004 seconds for 10,000 data. You can see that you can have XW, and you can see now that it execute the fast Fourier transform when your number of data doesn't have to be order of 2, which means that actually the real algorithm behind FFT Matlab is not have something pretty cool that is not gonna be within let's say that okay, they're not using Radix 2 directly. They need some modification, because Radix 2 you need to make sure that your n is in the power of 2, and now you know that in Excel format, Excel is directly using power of 2 as a number of data, so they follow the algorithm of Radix 2 Hurlituki directly. Okay, but in Matlab, because it's more commercial software, you n can be anything. Okay, so it's even more interesting to know. But actually in the real world, if you want to actually n is not in the power of 2, you can extend. For example, your n is 10,000. Okay, I can expand 10,000 to, you know that the 8,192 times 2 is become 16,386. So I can use the platform of 16,384. Okay, and why putting all the zero from n equal to 10,001 to n to 16,384, the time domain is become 0, and then use Radix 2 to solve it. It's gonna get the same solution here. Okay, but it took too much time. You can see that, because the original problem is only 10,000, but you have to solve the problem in the size of 16,384. Okay, so this one have something behind it, which is not only Radix 2. And you know that the fast Fourier transform is a very huge subject. Okay, and it can be taught in one semester. Okay, and then there are several variations of beyond from the Radix 2 idea. Okay, Radix R is the one that Radix 2, Radix 3, Radix 4 is the one that we stick with the classical idea. But there are way more variety of knowledge that you can explore and think, and certainly with those knowledge can help you to solve the problem that sometimes you require to have that knowledge, because all software have limitation, just like what I show you in the Excel platform. But you can see that Excel platform is limitation is caused by the software that you can run only 4,096 point as a maximum size problem. But in Matlab, okay, you can see that This is 10,000. Okay, I'm gonna do 100,000. Let's see what's the result gonna be. You can see even 100,000. 100,000 is a very large problem. It took what? It even took more time to generate the problem than solving the problem. You can see solving the problem still 0.02 and 30. So now you can see that I can go up to a million. Okay, a million point. For a million point, okay, it's gonna take some time now. Okay, but still, to generate the problem, when you want to execute this absolute random, it took longer time. It took 1.74, 1.75 seconds, and less than a second. You can see that you can execute and solve a 1 million fast Fourier transform. 1 million point in less than a second, even 20% of a second. Okay, you might say that, oh, I'm not going to use Excel anymore. You got remember that this is a very powerful software. Okay, but if I keep expanding a little bit, okay, I'm going to do like suppose I'm going to go with this one, 2000. Okay, 2000 million. Okay, you can see that those, okay, 2000 million. Okay, when n is 2000 million. Okay, I'm going to try to run it. Wow, it shows something already. When n is become large, this one is you approaching setting up a scenario that you have a big data scenario. Okay, when this big data scenario occur, okay, you see that, okay, the requesting solution of this one, the xt of time domain, require 15 gigabytes array that exists maximum array size preference. What is maximum array size preference? Maximum array size preference is that normally the software will check, once you install it, they will check whether your computer have available memory, and they will set up some default maximum array preference. But creation of array greater than this limit may take a long time and cause Matlab to become unresponsive. Okay, this is, you might say, is this the hour memory? No, it's not our memory. I think Matlab, and if they say our memory, they're gonna show you something else. Okay, but if I keep increasing this, maybe 20,000 million or 1 million million, okay, or it can be in the real world with the excessive of amount of data, it can happen. And with high resolution of sensor, okay, you can, the data can keep collecting and adding a very long stream of data. But in this one, let me tell you about the story when you're using a computer software. You can see that when we trying to solve the problem in the previous case, okay, here, okay, you remember that the first one here is a 10,000, very quick, 100,000, or even 1 million point. The 1 million point still look pretty good down here, okay, still look pretty good. Each of them very quickly responds, okay. But you can do that, see that once you increase to 2000 million, Matlab has some warning, not warning, they're gonna terminate you immediately. Then we say that with this amount of barrier, the system or the problem starting causing the software to perform, I call this as an uncomfort zone of hardware. So it means that when you're solving less than a million, like in this one, even the million, the case of 1 million, okay, even 10 million, I think still in the possible the comfort zone. The response is pretty okay. Based on my computer, and this value change computer by computer. If your computer have GPU, okay, you like to play game, you install the NPU, GPU. Sometimes this limitation can go further. Okay, so the software we check in this one, the Matlab check and say that 2,000 million is too much. Okay, too much is mean that when you execute this command, the object of FFT, it they just say may take a long time. And then they didn't even let you try. You say, and cause Matlab to become unresponsive. Unresponsive is mean that you see the clock, the sand clock that you normally they're gonna keep going on forever. In that situation is what we call your size of the problem cause the response of the software under your specific machine that you're using is reaching the uncomfort zone of problem solving. Okay, so this is a challenging one that we show you. Okay, based on this example. Okay, when you reach 2,000 million, based on my computer, didn't respond. But maybe the computer in your home have a very powerful CPU and have a large amount of RAM, the memory, read, uh, the random access memory. Okay, so even you checking with me like this, reach what we call the 1 million. Okay, you can start with 10 million, 100 million, and then 1,000 million, and then 20,000 million. Maybe if your computer is very powerful, or you bought some server and you run it under a very high memory and high power CPU. Okay, you might be able to run the 2,000 million still in the comfort zone. But if you keep expanding this one, just like what we did in this program, at one point you're gonna meet what we call this thing that can happen. Okay, can happen that appear on the screen that I show you. Okay, and that will be the assignment, the last assignment of this course for your take-home exam. Okay, and before we go through that, okay, in this part I already just want to show you that the continuation from the previous part is that you'll be able to solve a large Fourier transform, not really large just like what we are doing in Matlab, but far beyond, many times larger than the limitation of Fourier analysis in Excel. And then we taught you the strategy based on using the knowledge of radix tool, okay, and apply it to be able to solve a larger problem. And then we also keep expanding the radix tool to radix 3, okay, and show you an example and gave you a take-home exam, okay, and you can check whether you did it correctly, you do it correctly by using this Matlab. But we now are doing it again with Matlab. That but the uncomfort zone, okay, is much larger, much more efficient. We show you in this one that even the size go up to 1 million, is still the software still be able to respond. Okay, but up to 2,000 million, no, it cannot be. Okay, so that's the I'm gonna stop the Matlab part at this moment. Then now you know that you can do it on Excel platform, and then you can check your results for a large scale problem with the Matlab environment. And now you know that how to expand and checking the limitation or checking the uncomfort zone of under the Matlab. Why in Excel they just the uncomfort zone you just know because their limitation is only 40,096 as specific from the software themselves. Okay, okay, we are now gonna come back here, okay, to the classical fast Fourier transform radix 2 of Kulitukki. As I told you before that, okay, the idea of Kulitukki, okay, you can check the original paper by going to the sub drive here in under this folder and check with this copy Kuli 65.pdf over here. Okay, this is the where it all starts. It's the original, okay, an algorithm for machine calculation of complex Fourier series. You might wonder, it's a Fourier series. It's not Fourier transform. What do you mean that this become what we call the algorithm called fast Fourier transform? So far we haven't talked about it, but you might be able to see it a little bit that why they call Kulitukki call this as a complex Fourier series. Okay, and if you go to this paper line by line, W is the same notation. Remember that this one W, and this AK over here. Okay, AK over here is just the term, okay, of the X. You might remember that X, this is a frequency domain, this one is a time domain data, AK. Okay, and then you know that they separated into two terms. Okay, and summation, and you know that with these two terms you can, that's the notation way back in 1965, and you might find it a little bit difficult to understand. Okay, but based on this, okay, this is one plus minus and all of that. Okay, uh, to be able to explain this clearly, this is the explanation, the same explanation as this one. Okay, okay, but I feel very fortunate that many people already simplify the original knowledge of Kulituki here, and we become, actually it's very short paper down here, and this one is summarize it over here. Okay, but we're gonna do it further, that okay, beyond this explanation of equation line by line of Kulituki's, okay, as this algorithm. Okay, we already show you here. Okay, but the best illustration graphically, okay, for the idea of Kulituki can be expressed as in terms of a picture, and in terms of diagram, and we all refer this diagram as a butterfly diagram. Okay, so I'm using KP. Okay, we're gonna talk a little bit about the representation of radix 2 of Kulituki in terms of butterfly diagram. Okay, and then for this problem, okay, I already prepare a few slides for you, and an Excel file. Okay, what we are doing here, we're gonna move down here, and then using this, okay, this tree file. Okay, start with this radix 2, the picture of radix 2. Okay, so what does this one mean? Okay, you might see a little bit. You remember that x bar k equals to summation n is equal to 0 to n minus 1 w to the n k times x bar. And this one is when n is equal to 8. Okay, capital, only 8 data. So n minus 1 is 7. So this is the original one we call x bar k. Okay, you might remember. Okay, this is what this is all about. Okay, the original DFT. Okay, and when you using this separation, okay, of radix to Kulituki, okay, that's the result. This is what we did here using Kulituki. You can see that n is 0 here become 3, 0 to 3, because n minus 1 is 7, and this one is coming from here. Okay, since n is equal to 8, 8 divided by 2 is 4, 4 minus 1 is 3. So this is just a substitution of this classical radix to Kulituki's. Okay, so is this one separate these two, the first term k, and k reducing by half, k star, this one k star and k star plus. You can remember that this become k star, k star. The original, this is k. This one actually I should alternate the sign. The first one k start from 0 to n minus 1. This one k reducing by half. And in this picture I just change, the original is k, this one become k star. Okay, and this one change this one. So it's just apply this formula directly to this two term. Okay, so k reducing to 0, 1, 2, 3. Okay, half here, and next star k, and this one k star plus the n divided by 2, n divided by 2, since n is 8 become 4. Okay, so this one just directly using this formula. And then we're going to expand these two terms, okay? Summation n equal to 3 of w to the 2n k star times x sub 2n. And this one, the second term is summation n is equal to 0 to 3 w to the 2n times k star times x sub 2n plus 1. Each of these, okay, if I separate two terms, okay, I call this term, okay, the first term, this one is a k star, a sub k star, and this the second summation term, the separate summation term, we call b k sub k star, okay. And we are doing the same idea of latitude by expanding a sub k star to two terms. So so from k star become k double star, okay, and reduce half of this one since the k star starts from 0 1 2 3. K double star reduced by half is only 0 and 1. Okay, so a k star star and a k star and the plus this one is 4. The amount of possible k star is 4, so it becomes to 2. Okay, this one becomes 0 1 and this. And this, from this is w to the 2nk become 4nk and 4n plus 2. And for n plus 2k, w times 2k star that doesn't rely on n. You can move it out here. So from this one, w to the k become w to the 2k star. And there's plus minus here. We did this for the first summation of ak and bk. And become change from k star, this one double k star. Okay, become a k star star, a and b k star star. Okay, so it become plus minus, and this one instead of wk, since summation is w to the 2nk, n changing to 2n. From n, this one become 2n, but this one original 2n, so they change to 4n and 4n plus 2. 4n plus 2 cause wk to become w to the 2k. And so it's an expansion. This 2 expand to this, and bk also have this 2 term. And now we almost done here, because at the end, okay, now each term consists only summation of two terms. Okay, summation of this, okay. Like the first summation here, n equals 0, w to the nk double star, this one k double star, times x for n. Actually, when you substitute n is 0, it becomes x sub 0. When you substitute n is equal to 1, okay, when n is equal to 1, okay, it's become w to the 4k, okay, times x4. But you know that when k star star is equal to 0, okay, so it becomes this form. Okay, when k star star is equal to 1, okay, when k star, it becomes w with exponent of 4n. But w is you might remember that w is what? W is e to the minus I 2 pi divided by. So w time when you look at here, that w have an exponent of 4n, okay, this one is 4n, okay. And now n 4 w to the 4, because n is equal to 1, okay. The first term is the same, and n0 is become, but the second term, when n is equal to 1, it becomes w to the 4, and when k is equal to the 1, w with exponent of 4, okay, you can see that w exponent to the 4 is what? 4, and you know n is 8, right? In this case, n is. So 4 times 4, 8, so it becomes e with exponent I pi, because the it's a 2 times 4 is 8, divided by n is 8, they become 1, okay. And e with exponent minus I pi, you already know it's cos pi minus I psi pi, which is equal to minus 1. Okay, when you know it's equal to minus 1, so the second term is become x0 minus x4. And then you can apply this to the other 4 terms, this 2 and this 2. This 2 term, this the same plus minus, and this. And for this one, it's become x2 plus x2, x2 minus x6. And this one become x1 plus x5 and x1 minus x5. And the last term here, okay, the last term is x3 plus x7, x3 minus x7. Okay, so this is an expansion that now for the original x bar k, you can now reduce it to the original. This, you remember, x0 to x7 is the original input of the time domain. Okay, so once you know this, okay, but this one is look a little bit too much equation, you know? And you can rewrite this equation in this diagram form. Okay, and we call this a butterfly diagram. And why? You can see that this is x bar 0, this is x0. Let's look at the last equation first. You can see that x0 plus x4 is equal to this summation, x0 minus x4 equal to this summation, x2, x6 altogether. Okay, so this is what we do here. You can see that x0, x4 plus x0 plus x4 plus and minus. You can see that plus 1 plus 1 plus 1 minus 1. So each of these in the first stage, okay, from x0, okay, and reaching this summation is just the way that you compute this formula. x0 plus x4 become this summation, x0 minus x4 become this summation when for different k star. Okay, so this one is the result. K is equal 0, k is equal 1, 0, 1, 0, 1, 0, 1. But now you have x0, x4, x2, x6, x1, x5, x3, x4. And once you get this summation, okay, you can find A0, A1, A2, A3, B0, B1, B2, B3. Okay, so by using this one, you can see that A K star, K star 0, K star equal to 1. Okay, from here, they just using this. Okay, but you can see now the difference is that now the K star, if K star is 0, okay, the multiplication W to the 2K is 0. Okay, W to with exponent 0 is equal to 1. But when it's equal to 1, it's become W to the 2 W square, W square, W square. Okay, and that's result here. Okay, you can see that. Okay, when k is 0, okay, a 0, you can see here a sub 0 here. When k star is 0, so this one is 0, this one is 0. So a star over here, a and a2, a0, k star a0 and a2. Okay, will be this summation here. Okay, okay, plus and minus. Okay, when k star, this one plus. Okay, this one you can see that x0 and x2, right? Y switch to 2. Okay, you can see that because it's moved here, 0 and 2. Okay, that plus and minus. Okay, and this is how you do it. Oh, sorry, that's okay. A0 is plus, A2 is plus or minus, right? You can see that plus, or these two plus together, these two minus. Okay, but when k is equal to 1, k star equal to 1, you need to multiply by w square. This one plus w square, this one plus and minus w square. A1 and A3. This one is a diagram is coming from this. Okay, this part. Okay, okay. You can see that when k star is 0, okay, directly, okay, you can use this multiply plus and minus. Okay, and with a0 and a0 and a2, right, this one, so a0 and a2 become plus and this one plus and minus. But for a1 and a3 become plus and this one plus, but you need to multiply this summation by w square, and this one plus and you need to multiply by minus w square. And then for B is similar, right? Similar to A because it's followed the same format here. Okay, but just move to this part. Okay, this the summation of the latter part and the last two part here. Okay, so that's why B is related to this one, x1, x5, x3, x4 plus B0 is related to B sub 2, B1 with B sub 3. But B1, B sub 3 you need to multiply W square in term of plus and in term of minus here. Okay, and with extend idea, okay, you can now reach after you substitute a star here, you can move it here, okay, and do some similar way to now you can relate this to x bar here. Okay, you can see that x bar here you have to move 4 position. Okay, this one is mean that with x bar 0 with a0 you move by 4 position, 1 2 3 4. A0 matching with b0, a1 matching with b1, A2 matching with B2, A sub 3 matching with B3, with B2 and B2, A sub 3 matching with B3, and all plus 1 plus 1. And this one you the plus 1, the first term, this one plus W square, and plus W to the 3, to the third. Why? Because over here, you can see that when K start to increase, 0, the first term 0, W to the 1, W to the 2, W to the 3, and plus and minus alternate to each other happen here. Okay, so the first one is plus, the second one is plus and minus, the second one plus, the second one plus, but this you need to multiply W to this term. So the fourth term will have the lag order for 4. Okay, the next one. Okay, and this one 1, and this one multiply W, this one 1 multiply W to the 3, and then for the latter part of, okay, once you know x0, x1, x2, 4, 5, 6, 7, okay, using this, okay, 4, 5, 6, 7 here become minus, okay, and that's you get 1 minus 1, this one 1 minus W time here, and then 1 minus W square time here, okay, and 1 and minus W, the cube of W times here, okay, and that resolve x bar 0 to x bar 7. And as you can see that this is why they call the butterfly diagram. Look at this linkage, okay, it look like a butterfly, right? And that's why they call it a butterfly diagram. Okay, and so this diagram is just an explanation of this term. I'm using a very easy case when n is equal to 8 and applying to the direct DFT formula, and based on the fast Fourier transform concept. And you can see that how the computation reduce, okay, because the stage of computation to reach from x0 to x star is reducing to only 3 stages. Okay, but if you apply the DFT directly, you have to go to n stage. So n, in this case, 8 stage reducing to only 3. Okay, when you move up to 16, it's going to reduce to only 4, which is 3 is a log base 2 of 8, right? Okay, when n is equal to 16, log base 2 of 16 is 4. Okay, so that's how the reduction of computation reduce that the number of stage to change from the time domain and frequency domain. In each stage require, you know, plus or minus up to the number of point. Maybe you can see from notation like you have n point. This one you have plus or minus n times, right? This the first time, the 1, 2, 3, 4, 5, 6, 7. So each of them have to plus or minus or multiplication up to at most the n times, okay, as a number of point, okay. So the computation in each stage is maybe n, the capital N operation of additive and multiplication, addition and multiplication, but the number of stage reducing, right? Instead of direct discrete Fourier transform, you need to have n stage, okay, for each k, right? For each k, okay. Okay, you n stage, because in one stage you need to compute n, it's the same, but to find this summation, okay, you need to sum it up n time, so it becomes n stage, a symmetric multiplication indicate, okay. But this one reducing to only 3 stage, so it reduced by 8 divided by 3 times, okay. And as n start to increase, if you study with the order of O2, okay, so it become n divided by log n of base with the base 2, okay. So if n keep increasing, the amount of times reduction keep reducing tremendously, okay. That's why FFT was so successful in terms of solving the problem, okay. And then I did some part on radix 16 here, okay. I show you, I'm doing on the Excel slide, which already available in this one. I just move you can see that the diagram down here is no, in this one is from time domain is in the left and frequency domain is in the right. But for this Excel file, I do it reverse. That I put the time domain here on this one and frequency domain here. So you can see that it has some similar. You can easily guess how it's gonna change over. Okay, like this one, instead of x0, x8, x4, x. You can see that from the previous here, the x0, x4, x2, x6, x1, x5, x3, x7. You can see that the whole first half is a all even term, right? 0, 4, with the subscript of even number, and this is a x and subscript of the odd number. Okay, so first they separate in half, and you can see that once n is equal to 8, this is separate by a half, x0, x4. You can see that from the Excel file is indicates some similarity. This one you expand it to 16. So you can see x0 expand on x8. And then why this one is not x2? Okay, x2 is become here because this 4. Okay, you can see that 0, 8, 4, 12, 2, 10, 6, 14. And this one 0, 8 corresponding to x1, 5, 4, 12. Okay, with 5, 13. It increased by 1 unit. Okay, 2, 10 related to 3, 11. And the last one 6 and 14 related to 7, 15. And then each of them pair plus or minus. This one is mean that only plus 1 or minus 1. The I think that the top one, the top part of the butterfly diagram is plus. The second part is plus and minus. Okay, just like what we found here in just like what we did here, plus minus. And this one start to plus, and then you multiply by w to the 2. Okay, you can guess that when you apply to in radix 12, it becomes w to the 4. Okay, which means that this one plus, and then plus, minus. The second one is plus, and this one is w to the 4. Okay, this one you need to multiply w with exponent of 4. This one is plus, and you multiply by exponent of w to the 4. But this one is minus. Okay, and now you have 4, right? This one you have 8 pair. This one you have 4, group of 4. And from group of 4, this one group of 8. Okay, from 16 to group of 8. This one group of 4, and then we come group of 2. This is just a half. You might remember this is a half part of the this diagram. Okay, and you half, but this one in each of them, okay, you start with 1 minus 1, and then 1 plus or minus w squared times the other term, and then w to the 4, w to the 6, because there are 3 terms. 1 w squared, w you have to multiply this one, the latter part. This is w to the 3, w to the 2, w to the w to the 6, w to the 4, w to the 2, right? Okay, and this one is w 1, just 1. Okay, minus 1 minus w squared minus w to the 4, then minus w to the 6, the same as the ladder. And this one certainly become 1, w1, w2, w3, w4. Okay, because of the notation. I think that if you understand this, the way that I explain this, and I explain this for n is equal to 8. Okay, it's the same things that, but I just give you the result immediately for this one. Okay, so you can see that the first part is even even subscript. Okay, and this is the odd subscript for the data. Okay, and moreover, okay, I gave you this in the file of the slide file of this radix 3 FFT that I already show you, and we explained it that we did it under the Excel format. Okay, already, right? And we also give you the radix 4, but we didn't implement it, but it's just an extension of the formula radix R. Okay, that we have it here. Okay, the radix R. Actually, you can keep extending to radix 5, 6, 7, whatever you want to. And but okay, based on this file, okay, we have two additional data picture that can give you. This one is a case that I took from the book. Okay, the book is in here. Okay, the book is from the related document. Is an ebook. This inside FFT back box here. Okay, actually, if you want to study the whole semester about FFT, what's inside there, okay, both in serial and parallel algorithm, okay, we still need to talk about how to execute this problem in serial and in parallel, okay, as part of the last assignment. Okay, the picture is taken from some pages of this ebook, okay. You might go back and take a look at where did I took it from, okay. Actually, there's a couple of paper that very but we're not gonna have time to cover it all. But if you might interested about this important technique, yeah. And also I gave you the Fourier Matlab. Okay, this is actually if you want to study what this FFT object can do for you, and there's some extension, okay, with some specific application. This is a part of the Matlab manual. Okay, and if you are interested, they even have FFT TX, okay, which is an extension. Okay, this is in the power of two. Okay, but to write it down in term of code, okay, divide and conquer, this is a purely radic tool, okay, command, okay. And I think that you can if you are interested, you can beyond what I did taught you in this class, you can go and extend to read this Fourier Matlab, okay, file, okay. But we certainly not gonna cover all of this, okay. But some of this is very interesting. The other one is 1 million FFT chips, okay, on single FPGA. You might not. This more like a electronic engineering. This is a paper that indicate that nowadays we can build a microchip that perform FFT up to 1 million point. Okay, okay. That paper just published way back. I think within not so long ago. I think you can check the year, 2019. Okay, 2019. It says work done in Sweden that there is more architecture of the electronic circuit. Okay, that they can build and a microchip of electronic circuit that execute the fast Fourier transform up to 1 million point. Okay, what we are doing so far, we are only doing in terms of software. Okay, availability and capacity of the software that offer you to solve the problem. But this one, they build hardware, okay, structure that can execute. So it means that you don't need to write any program, but just sensing the data less than 1 million point, put it in this electronic device, and they execute the result for you. Okay, no, you don't even need to write any program. Okay, so many good up to date, and some of them already outdated, but you can look at that as a basic for if you are interested, or in the future you might need to use more extensive knowledge of applying this tool. Okay, uh, okay, here I already explained this about the representation of the fast Fourier transform in the form of what we call the butterfly diagram. I encourage you to take a look at this case of the 36. Okay, no, 32. This one is extensive because we show you about 8 now, and this one is a 16. Okay, this one is 16. But now in this case it's 32. So x0 is coupled with x15, and then we move to x8 and x24. Okay, and this one. And the multiplication term is right here. Okay, they use omega instead of w. Okay, so pretty close to each other, and the notation. Okay, this one is that's why I built this Excel code. Okay, and put the multiplication for each arc here. okay, modular that plus or minus alternately, okay, this is W, okay, but in from the paper, okay, that the result is that they use omega, but certainly omega is also e to the minus I times 2 pi divided by n, okay. And so this is the result, okay, from the book, that based on the n is equal to 32. And we go back again, that why is this so important, and can we apply this further? It give you a better illustration of what we call give you a better illustration to explain you in this form rather than in this one. But this one is important. This one is actually is an explanation of how this diagram can be created, okay. But in terms of large scale, okay, we go back to the last time that we having a problem that for Matlab, you remember that we have that at one point, okay, when n start to be real large value, okay, you facing this type of situation, okay, that cause you the problem that you cannot use the object FFT directly. So it's the same situation that you in Excel platform, that you have a limitation of 4096. You can only execute up to 4096, but this one is a much larger value. Well, until they're reaching the uncomfort zone, the unresponsive zone, that the MATLAB had been predicted, and then they stop you continue any further execution. Okay, but we already learned under the Excel format already. Okay, so in the next script we will look more. I will give you some example of applying this knowledge, all the knowledge that we studied so far, to attack this type of what we call the big data FFT. Okay, and you might start to realize that is this possible to apply? This diagram is one way that you can offer to explain, because some of this x0, x4, x2, x6, xy, x3, and x7 doesn't have to be an individual value. It can be a large vector also. Remember that this one is only n is equal to 8. 8 can be a group. Suppose that for each group, okay, this one is separate in 8 group. This one is for each group contain 1 million point, for example, or 200 or whatever the number. Suppose each group contain 1 million point. Okay, 1 million. The x0 have million point, x4 have another million point, but it's not consecutive. The sequence have to start with x0 coming to x1. The first million point in time domain, the second group of million point of time domain is in x of 1, and in x of 2 the third group, and so on up to the last group of x of 7. If you rearrange the data like this, okay, and then you perform according to this operation, okay, along the way to get this result, you can solve the problem of 8 million, right? Because sub part of this is a million, okay. But the question is, do we have to go through this complicated network, or even more complicated when you consider using what we call the n is equal to 16, or even most complicated case that you can find is in this case of the 32, and you need to be able to organize many data structure, okay. And also you might think about it that, okay, if you decompose the large problem to a smaller problem, and you execute the smaller problem, and you know the relationship of the smaller problem that lead you to the sub part of the of the solution of this large problem, and then you combine sub part of this result together to get the overall solution of the big problem. So that's the whole issue here. But this butterfly diagram can also be applied. But does it have to be necessary to go to all of this? Because As you know that once you execute a million point, it took less than a minute, only 20% of a minute. Okay, you might not need to go to like, okay, for example, if you have 20,000, let's say you have 1,600. Okay, each of them will be 100 million point, each of them. No, 200 million. For each of these 200 million point, x0 have 200 million point, x of 1 have 200 million point, the next, and overall you have 16,000. Okay, less than 2,000. If you go to calculation using this flows of data of butterfly, you get the result here also. But as you know that Matlab is not comfortable with the memory that you put all of this all together. So therefore you need to manage your secondary storage of your computer, which is your hard disk, your SSD, or any further secondary storage that you're using, maybe the cloud storage or whatever. Okay, and you just need to retrieve and one group of data at a time to execute the result and put it back to the secondary storage, while you maintain the main storage to be able to execute the sub problem with the comfort zone of responsive results. Okay, so this is the whole idea. But what the example that I will show you, that we will not try to do this, apply this butterfly diagram. We will only use the radic R formulation. Why? Because in this butterfly diagram, okay, it still consists of both parallel. Parallel is mean that like this four can be performed independently, but you have to be performed before you can execute to get this. Because so it's both sequential and parallel containing all together in here. And once the sequential operation still exists, it's gonna cause you to wait, because you can't go on without finishing your predecessor job. Okay, so in this one, you have to perform this, but this four you can perform independent to each other in parallel, right? So for example, you have four computer, you can perform this x4 x2 x in four computer. Okay, but once you finish this, okay, for each of this you have another four butterfly. You see, you use another four to compute the other four butterfly, okay, in the second stage, and the last four butterfly in the third stage. So you have four machine. Okay, suppose you have four computer, you can execute in parallel in each state for one specific problem to get the result, and then you continue to do it in three consecutive sequential stages. Okay, and that's diagram help you to look at that when you attack a large FFT or very long stream FFT that you cannot execute, facing the problem that you cannot use the direct object to solve the problem at one time. Okay, you can decompose it to smaller problem, and then using this type of knowledge to help you. But this diagram still have this advantage, is that it still contains some sequential operation. Okay, and but sometimes it can be benefit also. Okay, and that's the research that everything in the world, there's nothing that always disadvantage, always bad. It's good in some case, but it's not good in some case. But it's all dependent how you're gonna be able to look and find that what is the advantage of this approach gonna be in what situation. And that situation might be too ideal to happen, but in terms of knowledge, it's still, it's still a knowledge that, okay, if this thing happen, this could be better than the other alternative. Okay, so in the next clip, okay, we will explore more about the idea that you refer to here as a radic R, and we're going to apply this and set up some set of Matlab code that I developed you as an example, and we try to attack that 2000 million point. Okay, and that's going to be your last take-home assignment and as part of your take-home exam in this semester. Okay, So see you in the next script. Okay.